Greetings, Mick McQuaid here to introduce week 1, day 1 of iste780. And I'd like to begin by previewing the first chapter of the textbook. And the textbook is 10 chapters long, and it's about 9/10 about supervised learning. And 1/10, that is chapter 10, is about unsupervised learning. So it makes sense to ask what supervised and unsupervised learning are. By supervised learning, we are referring to data that has both an input and an output. And let me give you an example. This example is one that's explored in the textbook. It's an example of television advertising and sales. The input data is television advertising, and the output data is sales. We would like there to be, if we spend money on television advertising, we would like there to be a relationship between the amount of advertising that we spend and the amount of sales that are generated as a result of this advertising. So we have two kinds of sample data, input sample data and output sample data. And from this, we can make predictions and inferences about future occurrences. Unsupervised learning is different in the sense that we have only input data. We don't have output data. We have input data and we would like to learn something. We would like to actually, in some sense, describe the data. And there are some examples given in Chapter 1 of supervised and unsupervised learning. And there's some discussion of what we're actually doing. What can we do with all this knowledge we're going to accumulate in over 400 pages of and 20 days of intensive study. And there are basically three things to do, two of which are covered in Chapter 1, which are prediction and inference, and the third is description, which unfortunately doesn't get enough explicit coverage, but which is indeed covered in the course. By prediction, we mean predicting an output from an input. So, for example, we have the television advertising data as input, and we would like to predict, given some amount of advertising budget that we have, the amount of sales that we can expect as a result of this input. So that's a case of prediction. Inference is closely related. Let's say that we have input data and output data, and we would like to infer the relationship between them so that we know. See, in the case of advertising and sales, we may have some control over the future sales by modifying the amount of advertising in the future. But there are some cases where we don't necessarily have control. Like, let's take, for example, the wage data that is discussed in this book. So there's wages and ages. So we can infer that there's a relationship between wages and ages. We can't necessarily control someone's age, but we can infer what their wage will be as a function of age. And then the third thing, description, and this comes more into play in unsupervised learning, where we want to somehow describe the data. But if you leaf through the textbook, you'll find description on almost every page, every picture, every statistical graphic is a description of data. So description is pervasive throughout machine learning and statistical learning in particular. The book deals more with linear models than nonlinear models. And this is because history has dealt more with linear models than nonlinear models. Even though the world is not linear, there are lots of reasons why people have used linear models to model the nonlinear reality more than they've used nonlinear models. And there are all kinds of tricks that we know work very well for approximating nonlinear reality with linear models. So although we will explore both kinds of models, we'll actually spend more time on linear models. Now, the textbook has an ambivalent relationship to linear algebra, which first appears in Chapter 1. The textbook authors tell us that we don't need linear algebra in order to appreciate this textbook. But then they launch into quite a little discussion of linear algebra. So I'm going to talk through some of what I think are the most important points so that it will be a little bit less puzzling when the authors start throwing linear algebra terminology around without explaining it. And the first thing to say about that, because it's going to come up over and over again when we start programming in R, are vectors and matrices. So a vector in the context of this book is a column of numbers. You could think of it as a column in a spreadsheet. And a matrix is an array of numbers. You could think of it as an entire spreadsheet or as an array in a computer program. And most of the matrices that we deal with will have the dimensions n. There will be n rows to the matrix and p columns to the matrix. And what we mean by n is the number of observations. So in the case of the wage data, for example, it would be the number of people about whom we have wage information. In the case of the television advertising, it would be the number of markets in which we have that information. So the number of observations we'll always call n. And the number of variables we'll call p, and we'll have a somewhat ambivalent relationship, I'm afraid to say, with p. So generally by p we mean the input variables, but sometimes we'll also speak of p variables including the output variable. So we have one or more input variables and one output variable. Now let's take a look at some stuff in the textbook. The pictures in the textbook are particularly edifying. And the textbook begins with three examples. First, the wage data. And this is an example of a regression problem. So in this case, the input data and the output data could both be construed as continuous variables. So we would like to predict a continuous variable based on a continuous variable. And you could potentially even say that about the time or education level, even though these are much constrained, but at least they can be ordered. At least we can say that level 5 is greater than level 1. Year 2009 is 1 year after 2008, and so on. Much more difficult is a classification to assign an order to is a classification problem. So the second example that's given is an example of a classification problem where we would like to classify the stock market's movement as either down or up. I should say more specifically than the stock market, the Standard & Poor's 500 index as moving either down or up on a given day. And we can't order that. I suppose we could say that up is greater than down, but it doesn't really matter. And there are all kinds of categorical problems like this, where what we would like to do is classify something as one or another, or maybe one of several things, different colors, for example. If we want to classify things as different colors, it's difficult to place an order on them. The third example that's given is the unsupervised learning example. Here we have gene expression data, and I suppose in a sense you could say that there is output data here, because there are cases of people who have cancer and people who don't have cancer, and so you could say that what we would like to do is classify that, but what we really want to do is find out which of these genes are closely related to each other. And here are two different ways of classifying them that may be more or less realistic. Okay, and then I'm just going to skip over this history of statistical learning. It's quite interesting stuff, but it's not problematic. What's problematic is what comes a little later here, which is this notation in simple matrix algebra. So here is where they introduce the notion of n and p, and the number of distinct data points or observations, and p, the number of variables or dimensions, we could also say. And they show an example of a matrix. And one thing that I should point out in a matrix is that the way that we note a matrix is first by its row number and then by its column number. So x11 is in the first row in the first column, x12 is in the first row in the second column, and so on for p columns. And x21 is in the second row in the first column, and so on until we get to the nth observation. Each one of these rows represents an observation, and the very last one is xn1 through xnp. So that's a matrix, and matrix notation is going to require us to have these two subscripts, and they're always in the same order. They're always in row and column order. And matrices are almost always depicted with uppercase, boldface letters. That's a very common standard for depicting matrices, not just in this book, but in other books. Then there's the notation, which is peculiar to this book for vectors. And I say it's peculiar because it's typical to note vectors with a lowercase boldface letter. And here they're denoting a vector as a lowercase letter that is not boldface. Also, they're saying that by default they're columns. And so this requires us to know, so here we see a vector being noted. It says at other times we'll be interested in the columns of x, which we'll write this way. So here's an example of noting a vector as a lowercase boldface letter. And it only has j as a subscript because in this case we're talking about column j. Okay, and we may write out the matrix as being a series of vectors. So just as you might think of a spreadsheet as a series of columns in the spreadsheet, you can think of the matrix as a series of column vectors. And now they suddenly introduce the notation capital T, X transpose. This is X transpose. And the reason for this is that we often want to transpose a vector or a matrix. And here's an example of a transposed matrix X, where now the first, what for X would be row 1, column 2 is now in an unusual location. It's now in row 2, column 1. God, it's so confusing. And the same thing is true for vectors. So if we transpose a vector, instead of being a column, it becomes a row. Or if we transpose a vector that's already a row, it becomes a column. And this is going to become extremely important later. And I know it sounds, if you're not familiar with or you're rusty on linear algebra, it sounds kind of ridiculous. But it's related to an important rule, and here's the rule that is given right here. It is only possible to compute AB, this is multiplying two matrices together, if the number of columns of A is the same as the number of rows of B. So in this case, matrix A has 2 columns, and matrix B has 2 rows. What it doesn't say, there should be an additional sentence after this that says that the result will be the number of a new matrix that has the number of rows of A and the number of columns of B. And because they've very conveniently given us square matrices, we get this square matrix output. So this may not be obvious to you, but as soon as they start displaying vector and matrices being multiplied together, it will become unavoidable. So an important thing to take away from this is that the order matters. BA and AB are not necessarily the same thing. And just because you can multiply A times B doesn't mean you could multiply B times A. The commutative property of multiplication doesn't hold for matrices. The number of columns of A has to be the same as the number of, in other words, the number of columns of the first object here has to be the same as the number of rows of the second object. And the output will be of the size of the number of rows of the first object and the number of columns of the second object. Okay, so that's enough of linear algebra for the moment. In my next short video, I'll talk about the R language. Thanks for listening.